So you want to know what the geometric mean is. The geometric mean of two numbers is the positive square root of their product. Which product means, again, what operation? Multiplication. So I'm going to ask you, I'm going to give you two numbers and say, what's the geometric mean between these two numbers? And it's the positive square root of their product. Meaning that you're going to multiply them and then take the square root of that number. Okay? And then simplify it if necessary. Now, this is the formal definition, or this is the book definition of geometric mean. Okay? It's saying the same thing a lot longer. Don't worry about writing this down. I would just worry about this. Okay? It's a positive number, a, where in proportion a over x equal x over b. Meaning if you had a and b, you were trying to find the geometric mean between a and b, and you called it x. If you cross multiply it here, you get x squared equals ab. Then you would take the square root of both sides, and you care about the positive one. Square root of ab, which is just what we said up here. Multiply the numbers, take their square root. That's what the geometric mean is. Now, why is the geometric mean important? It'll come up in just a second because it's in one of our theorems. You will have a postulate sheet for this chapter. I don't have it right now, so any of the theorems don't worry about writing down because they'll be on there. Yeah. The geometric mean is a positive square root of their product. Meaning, if I wanted the geometric mean between 2 and 50, okay? So to find geometric mean between two numbers, it's the positive square root of the product. What's the product of 2 and 50? Product meaning multiplication. 100, right? And it's the positive square root of that. Which actually, 100 is a perfect square. Its square root is 10. So the geometric mean between 2 and 50 is 10. I just did the positive square root of their product. Yep. That's the answer. That's what the geometric mean is between 2 and 50. Okay? This isn't always a perfect square. If it's not, you just simplify it just like you did on that sheet. Okay? Let's look at another one. Like this one. I left the answer there. Okay. So, I want the geometric mean between 25 and 7. Go ahead and try that first, and then we'll check the answer together. All right, so let's check this one. So the positive square root of their product. The product, 25 times 7, I want the square root of that. Okay. Which, the answer to this, if you take 25 times 7, is what? 175. Good, it's 175. But actually, since it was already written like this, I could actually simplify it from here, right? If you did it to 175, that's fine, but I know this is the same thing as that, right? Multiplication problem, I can break it up. And because 25 is a perfect square. 25, the square root of 25 is 5. 7 doesn't have a perfect square. So that's my simplified answer. 5 square root of 7. Okay. Now, on your calculator, one way you can check your answer. So let's say you don't know how to do calculator, or your calculator can't do simplified square roots. One way you can check your answer, okay, if you know the answer is 13.2, okay, is do 5 times the square root of 7 on your calculator. It should be 13.2. Okay, which is the same thing as doing square root of 175 on your calculator. Okay. Again, right now I want you to simplify them. On certain problems, it will be okay to have the decimal. Okay. But right now I want you to be able to simplify them. So that's the geometric mean. Okay. Any questions with that? No, right now this is all I care about, the simplified square root. On certain problems, though, when we talk about length and stuff like that, it'll be okay to have the decimal. Okay. Which then you just punch it in your calculator. But right now, just simplify the radical. Okay. Between 3 and 12, we won't go through this one. We know it would be square root of 36, which is 6, right? Multiply those together, take the square root. Okay. All right, so now we have 3 theorems this chapter. Here's the first one. You don't have to write this down because it'll be on your postulate sheet. Okay. And all this is saying is that if you have an altitude, remember an altitude goes from a vertex to the other side at 90 degrees. If you have an altitude of this large right triangle, okay, if it goes to the hypotenuse, it breaks the triangle up into 3 similar triangles. Remember, similar means bigger or smaller scaled versions of each other. So meaning this altitude breaks it up into that blue triangle is similar to that red triangle, which is similar to that yellow triangle. It breaks it up into 3 similar triangles. So obviously the red is the smallest version, the blue is the medium version, the yellow would be the largest version. This altitude breaks it up into those three similar triangles, which is useful because if I give you just certain pieces of one triangle, you can find the other pieces of the other one because you know they're similar. So there's our similarity statements. Okay. So the altitude breaks it up into similar triangles on your postulation. The next theorem, okay, has to deal with geometric mean. And you know how to find geometric mean now. It says the measure of this altitude, so this YW in this case, this is your altitude. The measure of that is the geometric mean between the two segments that make up the hypotenuse. Meaning it's the geometric mean between that piece and that piece. So if I gave you how long the red piece is and how long the green piece is, if you found the geometric mean between those two numbers, it would be this yellow piece. It would be YW. Okay. You only need those two pieces to find the geometric mean of the altitude, or to find how long the altitude is. So that theorem is very useful. All right. So I would like you to try this. You just sketch this out real fast. There's the answer. Okay. I want you to find CD in this figure given this information. I'll give you a second to try that one. So here what it gives us is it says BD is 6, so this piece is 6. AD is 27. Okay. And then I'm looking for CD to measure that altitude. Okay. This is directly from that last theorem, 8.2. It says the measure of the altitude of that large right triangle is the geometric mean between the two segments of the hypotenuse, between the two segments of that longest piece. So that one's 6, that one's 27. So the geometric mean between those two numbers. Okay. When you do 27 times 6, it's 162. And 162 actually breaks down into 81 and 2, right? Which is the same thing as that. And even if you factor this in this case, you should get the same thing. Square root of 81 is 9. And I'm left with 2 there. So this piece is 9 times the square root of 2, CD. If you want the decimal, I think it comes out to, what does that say? 12.7. If you do 9 times the square root of 2 on your calculator, or if you just do the square root of 162, it should come out to about 12.7. That's how long that piece is. Pretty straightforward theorem. But we can find another piece of the triangle only knowing the two segments of the hypotenuse. Questions with that? The last theorem in this chapter, 8.3, is a little more complex, but there's multiple ways we can do this here. Okay. It says if you have an altitude of a large right triangle, just like we have here, okay, that you can find one of the legs of this triangle, of the large one. So you can find either this leg or you can find this leg by taking the geometric mean of the hypotenuse, which is the largest side, and the piece of the hypotenuse that touches that leg, or that's adjacent to that leg. So what I mean by that is if you want to find YX, that piece of that right triangle, that large leg of that right triangle, right? That's a leg, that's a leg, this is the hypotenuse. I know it's the hypotenuse because it's opposite the 90-degree angle. Again, I'm looking at the big triangle here. If you want to find that piece, all you have to do is take the geometric mean of the entire hypotenuse and the piece of the hypotenuse that touches that leg. Does that make sense? Okay. That if you want to find this green piece, you take the geometric mean of the yellow piece, which is the entire leg, and the red piece, which is the piece of the hypotenuse that's adjacent to. Remember, adjacent means next to, that touches that leg. The same thing goes for the other leg of the triangle. If you wanted to find that leg of the triangle, okay, you can find the geometric mean between the entire hypotenuse and the piece of the hypotenuse that touches that leg. So if I found the geometric mean between the yellow piece and the blue piece, that would be how long that leg is. that make sense? Kind of more complex here. So that's all the theorems in this chapter, because what those do, and we can use similar triangles instead. I'll show you what I mean by that. So if I gave you this figure, all I did was I gave you two pieces. This would be a good one to sketch out. I think this is the last one. Okay. That I want you to find x and y, and all you know is the hypotenuse of the large side and one leg of the triangle. Now, we can actually end up finding all of the sides of this triangle, which we're probably going to do. The homework assignment, I think, is like just 6 or 7 of these type of problems, and then like 3 or 4 just geometric mean problems. But problems like this where I give you a triangle and I want you to find a couple missing pieces of it. Okay. So, there's multiple approaches we can take here. First of all, I know that x and y together have to be 9, right? That's what that tells me. It tells me the whole thing is 9. So I know if I find one of them, I can find the other one pretty quickly. Okay. I could actually also find, if I called it z, I could find that side of the triangle pretty quickly. How could I do that? Just look at the big triangle. How could you find that piece pretty quickly? By what theorem? Ringing a bell. Remember Pythagorean theorem? Pythagorean theorem says if you have a right triangle, okay, call it xyz, that if you take one leg squared plus another leg squared, it's equal to the hypotenuse squared. So if I take one leg squared plus another leg squared, it's equal to hypotenuse squared. Again, it's always equal to the side that's opposite the 90-degree angle. So if I looked at this giant triangle, okay, just a big triangle, meaning I kind of ignored this stuff on the inside right now, and I kind of ignored that. If I took z squared plus 6 squared, it's equal to 9 squared. Right? I could find that side. It didn't ask me to, but the ones on the homework may. So that would be z squared plus 36 equals 81. Subtract 36 from both sides because I'm trying to solve for z. Gives me z squared equals 45. And finally, I'm trying to solve for z, so I want to undo this squared. So the opposite of squaring something is taking the square root, right? Take the square root of that, those cancel. Take the square root of that. When you take the square root of something on both sides, you usually have to write plus and minus in front of this, but we don't care about the minus part, so I will just have square root of 45, which we know we could simplify if we want. 9 and 3, 9 and 5, not 3. 9 and 5, the pair of 3's, so one of the 3's will come out, and I'm left with 5 on the inside, so this is the same thing as 3 squared of 5, which is that piece. So I found that piece of the triangle, even though it didn't ask me to, but that's one way I could do it. So back to the original problem here. Again, I want x and y. Okay. What? Yeah, the 3 squared of 5, I just labeled it that side. That's what I found it as. Okay. One of the theorems says that you can find this piece by taking the geometric mean of this and this. But I don't know either of those. So I can't find this piece yet. That's what the other theorem of the chapter says. The last theorem we did, okay, said that you can, this piece is the geometric mean between the whole leg and the piece of the hypotenuse that touches it. So if I found the geometric mean between 9 and x, it should be 6. Meaning that 6 is the geometric mean of 9 and x. Right? That's what that last theorem says. It says if you take the geometric mean between the hypotenuse and the piece of the hypotenuse that touches that leg, it's equal to that leg, which I already know what that leg is. It's 6. So looking at this problem, what does this square root have to be so that it spits out a 6? What does this entire thing have to be? Has to be 36, right? So what does x need to be so that that's a 36? X is 4. Right? Again, I used that last theorem we just talked about. Okay. that said one leg of the large right triangle is the geometric mean between the hypotenuse and the piece of the hypotenuse that touches it. I just happen to be missing that piece. Okay. So I know now that this is 4. Which meaning I should be able to find y very easily. What will y be? Y would be 5, right? Because the whole thing is 9. And since that piece is 4, that would be 5. So actually the only part of this problem that I'm missing is that piece. Right? So the second theorem of this chapter said this altitude is the geometric mean between what two numbers? Between 4 and 5, right? It's the geometric mean between these two numbers, the two pieces of the hypotenuse. So I would say if I call this z, z is equal to the geometric mean of 4 and 5, okay, which is square root of 20, which simplifies to 2 square root of 5, I think. So that means this piece would be 2 square root of 5. Again, this was 4, and this was 5. So I found all the pieces of that triangle just knowing that piece and that piece to start with. And that's what you'll be doing on the assignment. Does that make sense? One other thing you could do in this problem, so this will be the last thing I show you, is you could use similar triangles instead. Meaning if I went back to the original problem, the very first theorem we talked about said this piece breaks it up into 3 similar triangles. Breaks it up into 3 triangles that are bigger in scale and smaller versions of each other. So I'm going to kind of break apart those 3 triangles. And I'm going to turn them all the same way. The small one, the medium one, and the large one. And let's label them. Again, my right angle's down here in the corner. So the small triangle, I broke this apart. This piece was x, right? And this piece was 6. The medium triangle, I know the long leg is y, and that's all I know. And the largest triangle, I know this piece is 9, and I know this piece is 6. So see what I did there? I kind of broke them all apart. I turned them all the same way so they're facing the same way. And all 3 of these triangles are similar. That's a bigger version of that one. That's a bigger version of that one. They're just scaled up, scaled down versions of each other. That's the first theorem we talked about. And I could easily find x this way. Let's say you didn't like what we did before and you want to do another way. You could easily find x this way. Okay? Because if you compared this triangle to this one, if you use proportions, you could find x. Meaning if I took the hypotenuse of the little to the hypotenuse of the big one, that's equal to the little leg over the little leg. See what I did? I compared this to this equals this to this. That's what we did last chapter, right? And you can solve this for x. Cross multiply. You get 9x equals 36. Divide both sides by 9. You get x is 4. And then that's just what we got before. So you can always break those 3 triangles apart, turn them the same way, label them, and then just compare sides with proportions. You can also do it like we did before.